This chapter on chemical reactions is honestly one of my favorites of the entire year. We've looked at chemical reactions in the past so that we know a new substance should be produced with new properties. In the lab, we're always going to be looking for evidence of a chemical change, things to look for, any kind of an energy change. Energy change. A chemical reaction will always be accompanied by some kind of an energy change. Exothermic, where energy is released, or endothermic, where energy is absorbed. You might see a color change. Now, sometimes the color change is kind of tricky because it could be the result of a new product, and the new product has new properties, and one of those new properties is that it's a different color. Or it could just be that you made a mixture. Like if I had a yellow solution and a blue solution, I could mix them together and get a green solution. And then we kind of have to ask ourselves, well, is this color change resulting from the formation of a new product, or is it just that we made a mixture? Other things that I would look for might be gases or bubbling. A gas produced. One of the labs that you'll do in this chapter involves a series of copper reactions. And throughout the lab, all you have to do is record your observations. It's a piece of cake. But sometimes people will say, there's no change. I don't observe any chemical change. But as I look at their beaker, it's fizzing and bubbling. Yeah, there's a new product in there. A gas is being produced. That wasn't there originally. Kind of the same thing with this option, a precipitate. A precipitate is formed. Now in chemistry, precipitate does not mean water droplets coming down from the sky. A precipitate is the solid formed from a reaction. I should say formed from reaction of solutions. So you mix two solutions together. And the solutions would be in the liquid phase. And then all of a sudden you get like this cloudy solid. It could be kind of chunky, or it could just be kind of a fine particle. But it's a new product. So again, people will say, there's no chemical change. I don't see evidence of a chemical change. My solution just got cloudy. Oh, but give it a second. That cloudy solid will sink down to the bottom of your beaker, and then maybe it's a little bit more noticeable that there is a new product being formed. So all of these would be things to think about in your when you're in the lab and you're trying to note any evidence of a chemical reaction. These labs in this chapter are seriously some of the best of the whole year. Eventually then we'll want to look at the reactions qualitatively in the lab. What are my products? What are the new properties? But then we'll want to be able to write and balance their chemical equations. Which again, I know this is something that you've done before. This is not the first time that you're seeing a chemical equation. But you may not have seen them for a while, so it's worth a little review. My reactants are often on the left side. My products are often on the right. They don't have to be. The arrow will just always point toward the products. You could have one reactant, you could have 10 reactants. You could have one product, you could have 10 products. There is no number of reactants or products that we have to keep to. Energy could be on either side. It could be a reactant or a product. If energy is a reactant, you have to add energy. The reaction is endothermic. If energy is a product, it's exothermic. Energy is released. If you look at a chemical equation as symbols, you'll see two different kinds of numbers. The little numbers within the formula, those are called the subscripts. You cannot change the subscripts when you eventually balance a chemical equation. The subscripts are there to prove how the bonds form. It could be that, in this case, H2O, they're covalent compounds. Oxygen has 6 valence electrons, needs 2 more. Hydrogen has 1 valence electron, needs 1 more to fill the outer shell with 2 electrons. In this case, they'll share, so that hydrogen can share a pair, and oxygen will share twice with each of the hydrogen. Or if I have an ionic compound, maybe I have something like calcium chloride, where calcium's charge is +2 and chlorine is -1. Well, it's because calcium would like to donate 2 electrons. Chlorine would like to take 1. If I have 2 chlorine, I can transfer both of the electrons from calcium, make a neutral compound. Those little subscripts will never change. They prove how the bonds form and how the atoms get a full outer shell. What you can change are coefficients. Coefficients are the larger numbers out in front that really just show us a ratio. How many particles of hydrogen, oxygen, water are either consumed or produced in this balanced equation. You can change the coefficients to balance the equation, but you cannot change the subscripts. There are different ways that you can read the coefficients. You could read it as a ratio of particles. So I could say 2 molecules of hydrogen react with 1 molecule of oxygen, producing 2 molecules of water, and that is totally acceptable. So these could be interpreted as a ratio of atoms, or in this case, molecules. However, eventually when we go in the lab, and let's say I want to run this reaction in the lab, I can't pull out 2 molecules of hydrogen from the air, and I can't find just 1 molecule of oxygen, and I can't like smash them together and make 2 water molecules. And it's just not realistic. We can't work on such a small scale in the lab. So in the lab, we work with a larger ratio. And we can think of this as a mole ratio. The mole will never leave you. It's going to stalk you for the rest of the year. Which, I mean, moles is just a unit that's used to represent a quantity of particles. So you could read this as a ratio of 2 moles hydrogen plus 1 mole of oxygen, forming 2 moles of water. You could do that. I mean, again, a lot of people, when they balance these, they read it as 2 molecules of hydrogen, 1 molecule of oxygen, which is totally fine. There's nothing wrong with that. Until you want to go in the lab. In the lab, now that becomes unrealistic. But you could use moles. So I could have 2 moles of hydrogen. That would just be 2 times 6.02 times 10 to the 23rd particles, or like approximately 12 times 10 to the 23rd, or 1.2 times 10 to the 24th molecules. But you see how we're keeping the ratio of particles consistent? If I have 2 moles of hydrogen reacting with 1 mole of oxygen, I have twice as many particles of hydrogen. The ratio in the balanced equation will always tell us how these reactants react and how the products are formed. On a larger scale, let's use moles. We're still keeping the ratio consistent. If I form 2 moles of water, I have a 1-to-1 ratio between hydrogen and water. And for every 1 mole of oxygen, I get 2 moles of water. I get twice as many particles of water. Now here's the other thing that's great. In the lab, again, we can't really count atoms or molecules in this case, as 6.02 times 10 to the 23rd oxygen molecules. I can't count that, but I can use molar masses. So I could say 2 moles of hydrogen. Molar mass of H2 hydrogen, maybe to make it simple, let's just say about 2 grams. 1 mole of oxygen. O2 oxygen, maybe about 32 grams. 2 moles of water. Again, if we just kind of round them, let's say water's mass is about 18 grams. Here's the best part about using that ratio as a mole ratio. Now this I could measure in the lab. I could go in the lab and get you 4 grams of hydrogen and 32 grams of oxygen. And I could make 2 moles of water, which if each mole is about 18 grams, 36 grams of water, I could do that. And look at the other thing that's really cool. The law of conservation of mass says that in a chemical reaction, you cannot create or destroy atoms. So look at the initial mass. If I add the total amount of hydrogen, about 4 grams, plus the 32 grams of oxygen, I get like a total of 36 grams on the reactant side. Check out the product side. 36 grams of product. It's the best. So on a small scale, it is totally fine to read that as a ratio of atoms or molecules. But when we go to the lab and we're working on a larger scale, we're going to also use that as a ratio of moles. It's a good thing.